Hi there. I'm going to show you a number of real-life grounding mistakes I ran into in the past 30 years. Some of these mistakes were really expensive and all of them were really simple to prevent. So I hope you will learn from this video. So why is grounding such a big deal? Well, let me give you an analogy. If you want to build a skyscraper in a swamp, everybody realizes you will have to build a foundation right into the bedrock. Well, in electronics, your foundation is grounding and your skyscraper is your circuit. So you can imagine how important this is. Let's get started. So let's have a look at the first example. The first example is a car radio IC on an application board. Now this IC internally has an RF front end, some digital and some analog parts. And the rule that's being violated in this board is it doesn't have an unobstructed ground plane. Actually, it doesn't have a ground plane at all. So this is the actual board. Originally it didn't have this copper tape as a makeshift ground plane, but I put that on to see if that would fix the problem. So what you see here are the measurement results of this board with and without that makeshift copper tape ground plane. Now let me first explain what you're looking at here. So this is an FM radio receiver, and on the x-axis you see the tuning from 76 to 90 megahertz. And on the y-axis you see the SINAT. That's an audio measurement for audio quality. Now you can see here the SINAT is terrible. You want all your SINATs to be at 43, 44. And you see that for this example, it's just almost zero. There's no SINAT, it's all interference. Now what's causing this? The digital is switching, and harmonics of these switching frequencies will end up in the receiver input if you don't have a good ground plane. And that causes a reduction in SINAT. Now the red ones are the original board results. So you see lots of places where the SINAT is absolutely horrible. And the black one is with the copper tape, and you see a huge improvement by this makeshift ground plane. Now whatever possessed them to make a board without a ground plane, I don't know, but this happened in real life. 50 of these boards were made or something like that. So this was an expensive one. Now as you can imagine, it's not really a practical solution to put copper tape on all these boards. So I actually made a really good two-layer design where I'm following all my RF design rules and grounding design rules, and you see that board here on the left. Now you're probably wondering, what does that do? These are the results of those two boards. Now the yellow markers are the original board with the copper tape, and the purple ones are the two-layer. So you can see that on all of these frequencies it improves quite a bit further, but you see that the biggest step is made by just adding a ground plane. It's absolutely the most important thing. Let's go to our second example. It's an FM radio IC for mobile devices, and the violated rule here is to give each ground connection its own via. Now here's the situation. You have a radio IC again with an RF front end, a digital and a PLL. And those three blocks have a separate ground connection. Now let's have a look how this was solved inside the layout. So here you see the layout. You see those 1, 2, 3 ground balls and a single ground via. And that's the problem. One of my main rules is give each ground connection its own via. Now how does this work out in practice? The schematic would look like this. So interference coming from the digital and the PLL will go through this via. This via will have an impedance, so you will get a voltage here. And this voltage will enter the RF front end, which will then cause interference. The IC designers knew about this problem, so they gave it 3 ground balls, but as I said, they're not used in the layout. So what kind of damage does this do? Well, sensitivity is 90 microvolts on one of these clock harmonics and 8 microvolts next to clock harmonics. So you lose more than a factor of 10 in sensitivity due to the fact that you got a single ground via instead of 3. So what is the right solution? Well, I've basically drawn it here with my excellent drawing skills. So 3 separate vias for each ground ball, and that solves the problem because you don't have a common impedance anymore. Of course, it goes to a ground plane, and you can say, yeah, that's a common impedance, but the great advantage of planes is it's the lowest possible impedance you can make over the entire frequency range from DC to infinite frequency. And the way this looks in the schematic, if you would represent it, you would see a small via impedance at each ground connection, but they cannot cause crosstalk anymore. So the interference is gone. So what's good to realize is making mistakes like this is actually incredibly expensive. So these first two examples were actually commercial projects. So imagine what happens if you make a mistake like this and you have a production run of something like 50 boards. You're looking at a delay of about a month. So you have to keep 10 people in a project on for 1 month longer. For an employer, that's easily 80Ks. Now, second, you need to start an extra PCB run, which depending on the board can get very expensive as well. And lastly, you may have a delayed product launch even due to this. So this is very expensive. So now how do you prevent all of these mistakes? It's actually very easy. I have 3 options I can offer you right now. If you watch all the movies in my playlist, which are about grounding and how to prevent grounding mistakes, they're very simple rules to follow. And I absolutely guarantee you, if you're not following them now and you start doing that, you'll improve your electronics designs overnight. It's extremely simple. If you want to go one step further, you can download my free product development checklist. It has a lot more points that'll help you. And finally, I'm planning to make a course somewhere in a 4 to 10 month time frame from now, where I'll give hands-on examples and teachings on how to make these kind of boards and products in such a way that they are right the first time and you avoid all of these interference problems. So those are the options you can take. You can look in the description for all the links. The next example is a car kit which had audio breakthrough problems. Now the situation is this: you have a PCB which contained the car kit electronics, a long balanced wire towards a microphone, and the violated rule here is to always have an unobstructed ground plane. Now what's the situation? With an audio breakthrough measurement, you put a lot of strong interference onto the whole setup, onto your whole setup. It includes the car kit PCB and the microphone and the wires. This very strong interference will be picked up by this long wire, goes into the car kit PCB and gets demodulated by the audio electronics. Now the way to deal with it is to simply filter it. This is the balanced microphone input and this is the input of the audio IC. And somewhere in between you put a bunch of small capacitors which basically short the RF radiation. That should really solve the problem normally. Now a colleague of mine came into my office with this board. He said, hey, I have an audio breakthrough problem. So I immediately saw that this used multiple ground planes. So this is the way it was done. Basically, the designer was aware of this problem. He thought, okay, I'm going to leave the interference on a separate ground plane so it cannot get onto my main ground plane. So you can see here it's a separate ground plane and the connection is here. And this thinking behind this was, I'm going to put this connection as far away from the wires as possible to keep the interference as far away from the wires as possible. And this is actually exactly the wrong way of thinking about it, because what you've actually made here is the following. These 2 capacitors were connected to ground, but in order for the ground return current to go from this place where the audio ground is to the ground of where these wires come in via these capacitors, actually the return current will have to take a detour. So this is one inductance, this path, another inductance is this path, and L4 is the inductance of this detour. Now the solution is of course extremely simple if you've watched my first few videos, because all you have to do is put a solder blob here. And the fix really took me like a minute. I scraped off some of the paint from the bottom of the board. Luckily the ground plane was available on the bottom layer, so I could very easily short it. Put a solder blob there, which basically kills all these inductances, because now the return current can go under the traces. The big advantage is that the total current loop, if you look at it 3-dimensionally, is the smallest as it can be. That's also the reason why ground planes are so incredibly effective at solving problems like this. I did that modification, he did the measurement again, and the problems were gone. So it's very important to realize that an unobstructed ground plane also implies no multiple ground planes. Always have a single ground plane. Never ever in my whole 42-year career have I ever seen multiple ground planes be an improvement. So keep that in mind. Now this is a very old one from the beginning of my career. I made this board in 1999 and it's a control board for the WSRT, which stands for the Westerbork Synthesis Radio Telescopes. At that moment it was one of the most sensitive receivers anywhere in the world. And this is the board I modified. The original board, which was made by an intern, had a 2-layer. Now you can see already that there are so many wires here going across this board. And you can see here that this has to go to another layer in order to get it connected, that if you make a 2-layer, there's basically no chance for good grounding. And the result was that if they turned this board on, then the whole telescope was basically completely overloaded with interference. So they asked me to fix it. So this is the first time I actually designed a 4-layer board. So I just made a 4-layer board with a good ground plane, unobstructed single ground plane with ground vias for each ground, which are my main 2 rules, flipped it back on and all the problems were gone. This just shows you how simple it is. It's really so simple to prevent these issues. So for the next example, I want to look at a custom FPGA board that I made for my high-end DA converter. Now you see the DA converter here. On the right, this is the total finished product. And on the left, you see the main board. And this is the FPGA board that I developed. Now I started off with an off-the-shelf board, but that had some basic problems. And I'll show those in the next video. I tend to go into that. So I thought I could get away with it, but unfortunately this was not the case. So this is the audio output spectrum with the off-the-shelf board. And this is the output spectrum with the board that I made myself. So you see a huge difference. And all of these were created basically by a non-ideal layout. Now, you cannot really expect one of these boards to be very clean because they're designed for digital purposes, not for high dynamic range analog RF or audio purposes. This is the actual board that I designed, and it was a lot tougher than I thought when I started. And this, I think, is an excellent example to use in my course to highlight how to get something like this done. And what made it very hard is that if I would have chosen a 6 or 8 layer with buried vias and things like that, or micro vias, this board would have been a piece of cake to make. However, that's extremely expensive. So I wanted to stick to a standard 4-layer standard process. And then I discovered it's extremely hard to get the power routing and the ground routing good enough. But as you can see with the result, this is the total spectrum. You can see how incredibly clean it is. You see some 50 Hertz harmonics here. You almost cannot get rid of those because, yeah, the grid runs at 50 Hertz and it's everywhere. And you see a little bit of distortion, but for the rest, it's completely clean. So here you can see the huge impact it makes when you specifically design a board for good ground and RF performance. And even though this is an audio product, which is low frequency, you still see the huge impact it has. Like and subscribe, or I'm going to make you an offer you cannot refuse. Whoa, who was that? That guy looked scary. Anyway, moving on. Next time we'll look at star grounding because it's regularly recommended on the internet, so we'll have a look at what it does. We'll look at multiple grounds in audio, which is also a popular advice, and we'll look at other sneaky layout mistakes, which at first hand look like a really good idea, but do not work out in practice. Well, hope you enjoyed this video and see you next time.